right, everybody. Hello and welcome to our next topic, which is the scientific method. You might be thinking, I already know what the scientific method is, and you might be right. You might understand the scientific method to a degree, but we're going to talk about it more in its practical sense, its practical application, and things you maybe have not quite considered about the scientific method. And we're also going to use this as a refresher for understanding hypotheses. Hypotheses are important. They're integral to the scientific method, and we will be formulating our own hypotheses in this class, so we really ought to talk about them. Before we get into the scientific method or hypotheses, we'll first talk about the aims of a study. This is a general term that we use to describe what research is intending to contribute. So this is different from a hypothesis. A hypothesis has a specific scientific purpose. Aims are more of a way of generally explaining what the goal of your research is. So aims are a clear statement about what the research intends to contribute, and it justifies why the research is being carried out. All research should have clear objectives, even if the objective is just to explore some idea. We talked a little bit about dreams in a previous lecture. Maybe you're just aiming to explore dreams, explore why dreams happen, or just some facet of dreams. It doesn't mean your aim needs to be so clear-cut that you're going to determine the cause of dreams. Aims have a different role than hypotheses, and they communicate what a study will provide to the field, to the general population, or to some specific field like education or business. So why are aims important? They're important because you often need money, for one, in order to do research. It's not always cheap. Take something like MRIs. I've done some work with MRIs. It costs thousands of dollars to run an MRI every day. It's very expensive. So to use a piece of equipment like that, you often need money or funding from people who write grants, like government institutions. So your aim should be clear. Your study should seem worth doing, especially if it's going to cost you some money. But we'll give some examples of studies that are not quite so serious. So what is a hypothesis? Plural hypotheses. So on to hypotheses. This shouldn't be your first time hearing about hypotheses, as you've taken statistics. So what is a hypothesis? Basically, it's a statement that serves as a basis for further investigation. So a hypothesis is not a question, it's a prediction. It's a statement, and it needs to be justified. There should be a reason why you formulated a certain hypothesis, and it will generally be because previous research has led you to have a specific prediction. So aims tell us why it's important to test the hypothesis and what basis or rationale there is for them. So they're related, but hypotheses are our real scientific piece, what goes into our actual research report. So we have two types of hypotheses. We have null hypotheses and alternative hypotheses. So if you can remember all the way back to statistics, we set up these two hypotheses so that we have mathematical opposites to each other. So when we run a statistical test, only one of these two hypotheses can be supported. And we use probability to do this. We will do a statistics refresher in this course. So if you're feeling a little bit like this feels unknown to you, don't worry too much. We will continue to talk about these topics, but at a very base level, null hypotheses suggest that there is no significant difference, no statistical difference between the variables in your hypothesis. The alternative suggests that there is a difference or that there is a relationship, okay? And remember that the alternative hypothesis is harder to support because statistically or probabilistically, whatever we set our alpha value to, or our p-value, hopefully some of this is coming back to us, that indicates our critical value and what we would need to find in order to reject our null hypothesis. So our null hypothesis is a sort of baseline. It's innocent until proven guilty. And the research hypothesis is often what we want to address or what we want to answer. And we need to find a certain level of confidence in order to support that alternative hypothesis. So again, we'll get to all of this in more detail. We'll continue to talk about this, but hopefully we remember at least a little bit about this mechanism of hypothesis testing and why we use these two different types of hypotheses. So other different types of hypotheses we can have directional hypotheses. We can say that we expect a positive relationship between two things or a negative relationship between two things. or that one group is going to score lower than another group on a certain measure, or higher, etc. We can have direction to our hypotheses. So instead of just saying that there's a relationship, we can say that there's a relationship with certain directions. So maybe we think that more screen time equals, let's say, leisure screen time, like watching TV and social media. More leisure screen time leads to a reduction in academic performance. That's a negative relationship. We could say that between men and women, we expect women to have more anxiety symptoms. That would be a specific and directional hypothesis. Okay. So here are some examples. I give a couple examples here. And examples of ways that we can say hypotheses differently. There's no complete template for a hypothesis, but we want to think about if we're including a direction or not. So here we have higher levels of attitude similarity lead to higher levels of abstraction. Do we think this is true? I think this is true. I think social psychologists would say that this hypothesis has some support. So examples of a null hypothesis here would be that there's no relationship between the two, whereas the alternative would be that there is a relationship between the two. Let's look at another. So more time around my dog leads to higher levels of happiness. I know from anecdotal experience, I know that that's true for me, using the word true loosely here, but I could make hypotheses here. I could say people who spend more time around my dog will be happier than people who spend less time around my dog. You can say exposure to my dog is positively linked with happiness. And this goes back to aims of the study, right? The aim of this study would only be to fortify the feelings I have for my dog. It would be difficult to get someone on board to fund this study if it required funding, unless maybe you're just doing general dog exposure. But nonetheless, it's an example of a hypothesis, a prediction that we're making. And if we want to add a direction or a specific prediction to our hypothesis, okay, here's what I think. This is a helpful chart, okay? A helpful chart to take a look at directional, non-directional hypotheses, and also a hypothesis that attributes cause or not. So if we take a look at a few of these examples, we have directional hypotheses that are causal. We could say more of A causes more of B, or non-causal. We would say more A is related to more B. So this is back to what we talked about before with the different types of studies. If you want to have a causal hypothesis, you need to run an experiment. And then we have non-directional hypotheses here as well. So I think that this is helpful. There are lots of different hypotheses that we can have. So when we formulate our own hypotheses, this slide might be a good reference for you. Okay, so why use hypotheses in research at all? Why do we use them? We use them because they inform us, so they're helpful. They guide our science. They guide our questioning and our understanding. So research can attempt to test a hypothesis, which it often does. It can attempt to explore hypotheses. Maybe we don't even know what type of prediction we want to make yet, but we just want to explore our options. Research can also attempt to generate more hypotheses or more predictions, which it often does. And it often does because our scientific method is a circle, right? You remember that from our little overview previously, hopefully. Okay, so again, maybe you've heard of the scientific method, but I want to draw your attention to a few things about the scientific method that we maybe haven't thought about. The scientific method is often presented as a set of steps. There's usually something like 6 or 7 steps, and then it's done. They say you do the steps 1 through 6, and then that's science. But in the grander scheme, the scientific method never really stops. The scientific process never stops or ends. According to the scientific method, we can always expand our knowledge on any given type, okay? So this is what we do, right? We would generally start at the top with an observation, come up with a question that we want to address, come up with a prediction for that question. We would run an experiment or a study, we would do some analysis, and then we would, come to conclusions all the way around about conclusions about our particular study. So oftentimes this is where the scientific method will sort of end when it's presented in textbooks. But the reality is, as soon as you make a conclusion, the idea is that other researchers in the field, or maybe yourself, will grab onto your conclusions and continue to expand them. And maybe you'll do that for another researcher. And we'll talk about a research report or how we write a research report in this class. And one of the last things that a research report talks about is the limitations of a study. what could have been done better. So other scientists in the field will likely pick up where you left off, or you'll pick up where you left off and start the process all over again. So I like to point this out. We don't spend a lot of time talking about each of these steps of the scientific method because it's something that I think has been driven into us usually at a young age, or at least I hope it has. If it hasn't, then familiarize yourself with it on your own time, but we do talk about it because it has greater implications here and now in this class, okay? So when we do our own research projects, we will follow this exactly. You'll have a question based on some observations that you've made or information that you've gathered. Then you'll come up with a hypothesis. You'll run a study and do some analysis and then draw some conclusions. So we will see this process in full. All right, so the 8 circles of scientific hell. This is something kind of funny that I like to talk about in this class. This is called the 8 circles of scientific hell. This is from Dante's Inferno, hopefully you've read that. This is about what we can do wrong, what we can do to interrupt the scientific method and the scientific process. So I'll talk about each of these generally just so you can see where we face issues in the scientific process. So we talked a bit before about published research, meaning that it's been peer-reviewed and deemed good by your peers. So we got limbo up top, okay, meaning that the science hasn't been published yet. And then next we have overselling, which is basically coming to a conclusion and then telling people it's the most exciting conclusion that has ever been found in all of science. And this seems ridiculous, but people do it all the time. You'll see headlines and news stories about research where we found the cure to this, when we come to find out that's not really the cure, it's just a step on the way to the cure of whatever is trying to be cured. Next, we have post hoc storytelling. Post hoc, again, something that probably was touched on in your statistics class, but post hoc testing is basically testing after your original hypothesis test. So some statistics have built-in post hoc analysis, like an ANOVA, where you're comparing multiple groups. That would be your initial analysis. Then you do a post hoc test to find specific group differences. But what this is really referring to is after going through the scientific method, after getting to your conclusion of your initial hypothesis, basically digging for something else, digging for a different story than what you originally had set out to find. Then we have p-value fishing. We'll talk more in the class about things like family-wise error rate, and that the more tests you run, the more likely you are to find significance. And that's what this is referring to. Basically running lots and lots of tests until you find a significant relationship, but not basing it in any type of question or hypothesis, just digging for some conclusion. Creative outliers means basically throwing data out that maybe shouldn't be thrown out. This is relatively common and not always good. Plagiarism, we'll just leave that at that. We know that plagiarism is bad. It happens even in the highest zones of circle. I'm going to post a video that kind of talks about some of these problems. Plagiarism is always a problem. Don't you dare plagiarize in this class. I will find you. Okay? Non-publication. This is a big and interesting issue as well, which is that scientific journals want to publish what's exciting. They want to find articles or reports that report on interesting findings. If you carry out a study, maybe you work on it for years, and you don't find anything that's exciting or anything that people might want to know about, maybe all of your hypotheses are not supported and you don't have anything necessarily new to share with the field. But the catch here is that even if you don't have anything necessarily new to share, if you share it, you'll save others from wasting the same time. But it can be very difficult to get research like that published. So this is a bit of a global issue here where research journals will turn away unexciting findings, even though those findings are really important to have out in the world. Partial publication. Same idea here, that you leave out some pieces of your research that would be informative to others. And then at the very bottom, the pit at the bottom of hell is inventing data, which also happens. People making up data to support claims that they want to support. And this is why the peer review process is so important and why replication is so important. If somebody makes up some data and someone else tries to repeat the study and can't replicate the same result, then we might know that something was wrong with the data to begin with. So I know that's a little bit of a lot, and you might be thinking to yourself, we kind of talk about the shortcomings of science a lot in this class. A lot of it seems very doom and gloom and everything that can go wrong. But knowing what can go wrong and knowing what can be done poorly or what can be done unethically is how you find the good. You have to be aware of how it can be done poorly or the wrong way, especially so that you don't end up getting tricked by it. Okay, which happens. The hypothetico-deductive model. So now we're talking about something called the hypothetico-deductive model, which is a mouthful. This is really another word for the scientific method, but we're using deduction based on hypotheses, whether they were supported or not, and then decide where to go from there in our line of research. So from what has been observed, hypotheses are proposed. Ideally, we use methods that would disconfirm or could disconfirm your hypothesis, and then we test and retest and we reformulate or remake the hypotheses. So this is basically saying that the anchor of the scientific method is the hypothesis. Whether or not the hypothesis is supported will inform what you as the researcher should be doing next. So that's what we're saying here, is that we should look for instances where the hypothesis fails, where our predictions are wrong. And then we can develop hypotheses that are based on that information. Okay. Something else to note here, we're going to come up with a hypothesis. I've said that a couple times here, but we're going to come up with a hypothesis based on some research that we read. We're not just going to go based on some hunch that we have, though oftentimes a hunch can inform a search for certain research. Maybe you have a hunch that people that engage in more online dating also have higher sociability. Maybe that's something that you think. You would go look up to see if anyone has confirmed or denied that particular hypothesis, and then you would formulate a specific hypothesis. So again, this hypothetico-deductive method, it sounds a little complicated, but it's really just saying that we base our scientific method on looking for hypotheses, basing it around where hypotheses fail and where they succeed. Okay. Oh, sorry, I already had that slide. And then just a little funny for you, something funny. Examples of funny hypotheses. Someone's digging for someone to come up with funny hypotheses for them, and then someone comes up with a hypothesis that they're not capable of producing their own work. So, I don't know. I thought it was funny. All right, but we should keep all these ideas in our head because, again, we will make our own hypothesis, and we want to make a good one. We don't want to make a hypothesis that we already know is going to be supported or not supported. We also don't want to come up with, a hypothesis that's doomed to fail. We want to come up with a hypothesis that is well informed by the research that already exists out there. Okay, so that's our bit on hypotheses and the scientific method. Please let me know if you have any questions on this, and I will see you next time.